Okay. In the last class, I said that the numbers in this column of this table were incorrect, but it turns out that they are correct. These numbers are correct. The second column of this table shows the entries of UK. Go back to the algorithm. This UK in the algorithm is the UK in line number 5. But lambda here, lambda k here, use the UK, use this UK, but this UK different from this UK, different from this UK. If you, I cannot write. Let me see. Okay. Now I can write. This UK is UK is divided in line number 3, A times U K minus 1. Recall that it is a vector V K minus 1 over the norm of vector V K minus 1. So the ratio lambda K here, UK, the ith entry over UK minus 1. The ith entry is this UK is here. So it is A times V K minus 1. The ith entry then divided by this number. And then over UK minus 1 is a VK minus 1. The ith entry over the norm of VK minus 1. VK minus 1. So the norm of VK minus 1 cancel. So this is equals to A VK minus 1, the ith entry over VK minus 1, the ith entry. So the numbers in the table should be equals to the numbers in the previous table. Yeah, let me see where the previous table. The table in, yeah, they should be the same. Yeah. This is the table from the previous example. This lambda is equal to A times V over V. So this table, the third column should be identical to the third column, the numbers in the third column of this the third column of this number of this table. This table is about the improved power method. Yeah, they are the same. Okay, same lambda actually. Okay, so in the last class I said that the numbers in this column were incorrect. I am wrong. Okay, they are actually, these numbers are correct. Okay. Yeah. I correct my mistake. Now, let's go to today's topic. Go to today's topic. Yeah. Okay. Today, I want to present two topics. The first one from section 4.3. It is about the QR factorization. It is a theorem, a well-known theorem. Then, based on this well-known theorem, I present the QR algorithm to find eigenvalues of a matrix. All the eigenvalues of a matrix, not, it doesn't like the power method. Power method only find the dominant eigenvalue. This is a section 9.5. The QR algorithm. Okay, now first topic one. Topic one. The QR algorithm. It is a theorem. This theorem says that every non-singular matrix A. I assume the matrix is a real matrix. The size is n by n. Every non-singular means the matrix has inverse. Every non-singular matrix can be factor as A is equal to Q. Q is an orthogonal matrix. Orthogonal matrix, orthogonal matrix. The definition is Q transpose times Q is identity matrix. When a matrix satisfies this equation, the matrix is orthogonal matrix. The properties about Q are the columns of Q are orthogonal to each other. And also the norm of each column is 1, okay? And unit vectors, yeah. When a vector, when a set of vectors the vectors are orthogonal to each other, and each vector, the norm is 1, the length is 1. We call that the set of a normal set, So therefore, the columns of Q, they form a set. That set is of a normal set. Okay, yeah, this is the definition of orthogonal matrix. Every non-singular matrix can be factored as an orthogonal matrix times an upper triangular matrix. Yeah, let me write this down. Can be factored as where Q is orthogonal. Yeah, definition is here. And R is upper triangular. Yeah. This is an upper triangle. And below the main diagonal line, all the entries are 0, 0. Everywhere is 0 here. Upper triangle. This factorization is not unique. Not unique. There are many cube, many arrow satisfy this equation. But if we require arrow, the main diagonal line, all the entries on the main diagonal line are positive, then this factorization is unique. This factorization is unique when the main diagonal entries of arrow are positive. This theorem is well known in matrix freely. Okay, freely. Okay, this is well known algorithm. Let me show you one example about this theorem. Okay, take a look at one example. Yeah. This is a example 1. Consider this matrix, a 3x3 matrix. Find the QR factorization of the matrix A. Find its QR factorization. Actually, the solution in this example is a typical algorithm to compute the Q factor and the R factor. Okay. Then how to compute Q? How to compute R? The following actually is the algorithm. Okay, to find QR factorization of any matrix A. Okay. Let me split the matrix A into columns. The first column are denoted by A1. Second column, A2, A3, third column. And also, I cut a Q into columns. Q1, Q2, and Qn. Because a Q is orthogonal, the columns are often normal. That means they are orthogonal to each other, and each column is a unit vector. And also I let R. R is an upper triangular matrix. It is R11, R12, R13, then 0, R22, R23, 0, 0, R33. Yeah. Upper triangle. And also I assume the 3 entries on the main diagonal line, they are all positive. RII, all positive. So according to the theorem, the QR factorization is 1 and only 1, unique. Okay, now what I want is determine the entries, all the entries in the matrix R, and also determine all the columns in Q. How to do that? Okay. Yeah. Step one. I first determine the first column of Q and the first column of R. QR factorization. So A is Q times R. Now A is A1, A2, A3, Q, Q1, Q2, Q3. And R is R11, R12, 13. Now I compare the first column on the left side and on the right side. Equating the first columns on the both sides of this equation. Then left side is A1 is equal to right side, right hand side. This matrix times this matrix, the first column is R11 times Q1. Right? The right side, the first column, the product, it is a matrix. That matrix, the first column is this. Now, what at this point, what I know is A1. I know A1, but I don't know R11. I don't know Q1. I want to find R11, Q1. How? Use the properties of the columns of Q. The columns are unit column. Then from here, I take two lambs on the both sides. Two lambs. On the both sides. And I assume, because I assume ROII all are positive, so I can move R11 outside the law. But matrix Q orthogonal. First column, the two long, this is two long, is 1. So therefore, R11. So R11 actually is the two long of the first column of matrix A. Yeah, the first two long, right? 1 square plus 1 square plus -1 square, then take square root. So it is a square root of 3. Now I know this. Now I know this. Okay. Now here, I know R11. Okay. Now how to get Q1? Move R11 to the left side. Then Q1 is equal to R11 times A1. R11 square root of 3. A1, the first column, it is 1, 1, negative 1. So 1 over negative square root of 3. 1 over square root of 3. -1 over square root of 3. Yeah. This is step 1. Step 1, I compare the first column of Q and the first column of R. Step 1. Now, step 2. Step 2, I compare second column of Q and second column of R. How to get Q2? How to get the entries in the second column of R? Now this time, equating this equation, equating the second column of the left side and the right side of this equation. Step 2. Step 2. Equating the second column on the both sides of equation. Let me give a name to this equation. Yeah, how about let me give a name to this equation. Equation, say equation 1. Okay, equation 1. Equating the second columns on the both sides of equation 1. Then we have left side is A2 is equal to, let me see, right side, the second column should be R12, this number times Q1 plus this number times Q2. R12 Q1 plus R22 Q2, right? R12 times this, R22 times this. Yes, correct. About this equation, what we know, A2, we know the second column of the matrix A. A12, I'm looking for A12, also R22. So A12, I don't know. Q1, I know from step 1. I got it, okay. R22, I don't know. Q2, I don't know. So in this equation, I want to find this number and this vector. How to get them? Use the orthogonality of the matrix Q. The columns of matrix Q are often normal. Okay, now let me get R11 first. How to get R11 first? Take inner product on the equation, this equation with Q1. I know Q1. Okay. Okay. Now we have Q1 dot A2 inner product. Take a review. A vector dot a vector is first entry times first entry plus second entry times second entry. The entry times the entry. Here I assume these two vectors are three-dimensional vector vectors. This is a dot product. When U is orthogonal to V, if and only if the dot product, inner product, is 0. This is a well known, okay, from linear algebra class, okay, course, okay. Now, yeah, I take inner product with Q1 on the both sides. Now the left-hand side is a Q1 dot R12 Q1 R22 Q2. By distribution, R12 times Q1 dot Q1 plus R22 times Q1 dot Q2. But because because the columns of matrix Q, they are orthogonal to each other. So this inner product is 0. How about this inner product? This inner product actually is equal to the length of Q1 squared. The length of Q1 is 1. So this is 1. So therefore, from this equation, we have R12 is equal to Q1 dot A2. Now I know Q1 from step 1. A2, I know second column of the matrix A. So I get R12. What is R12? Let me see. R12 is equal to negative 1 over square root of 3. Okay, now I know R12. Yeah, I know this. Okay, I know this. R12, I know. Now, next, let me determine R22 and Q2. From this equation, I move the first term to the left-hand side. So I get R22 times Q2 is equal to A2 minus R12 Q1. The quantities on the right side of this equation all are low now. Okay. Now take 2 norms on this equation. Take 2 norms. Because I have assumed R22 positive, so I can move R22 outside. And these are 2 norms. But the 2 norms of Q2, the second column of the matrix Q, is 1. This guy is 1. Yeah, this is 1. So therefore, I get R22 actually is the 2 norm of this vector. So this vector, I know. So this 2 norm is computable. Okay. Let me see. R22, what R22 is? Square root of 14 over square root of 3. Now I know R22. Yeah. Let me remove this question mark. Remove it. Okay. Yeah. I know this. Yeah. Finally, I determine Q2. How to determine Q2 from this equation? Right side, I know. R22, now I know. So from this equation, I get Q2 is equal to 1 over R22 times A2 minus R12 Q1. R22 is this number. So this is Q2 is 4 over square root of 42. 1 over square root of 42. 5 square root of 42. Yeah. So I remove this question mark. Yeah. I know. So step 2. I got here n should be the number 3. Okay, let me correct this. Yeah. This is a Q, only Q3. Yeah, Q3. Okay, now after step 2, I know Q1, I know Q2. and I know R1, 2, R2, 2. Of course, I know R1. Finally, determine the third column of Q and the third column of R. Now, how to tell them? Equating the third column of this equation, okay? Equation 1, third column, okay? Third column. This is step 3. Step 3. Okay. Equating the third columns of equation 1 to get A3 is equal to, let me see. This is equation 1. The third column of the right side should be this number times Q1 plus this number times Q2, this number times Q3. So it is R31 Q1, R32 Q2, R33 Q3. What unknown about this equation? What are those? Okay, I know A3, the third column of the matrix A. A31, I don't know. I need to determine it. Q1 from step 1, I know. R32, I don't know. Q2, I know from step 2, and I don't know this. I don't know this. Okay. Now, how to determine all the unknowns? Again, use the orthogonality of the matrix Q. Okay. Now, I take inner product on this equation with Q1 first. Okay. Q1 dot left side is R31 times Q1 dot Q1 plus R32 Q1 dot Q2 R33 Q1 dot Q3. Because the Q vectors are often normal, so Q1 dot Q1 equals to 1. Q1 dot Q2 0. This is 0. So therefore, we have R31 is equal to Q1 dot A3. I know Q1, I know A3, so this is computable. What the number is? Negative square root of 3. Let me remove the question mark. This guy, I know it now. Okay. I know this guy. Now, next, let me determine R32. This time, I take inner product on this equation with Q2. Okay. So Q2 dot A3 is equal to R31 Q2 dot Q1 and R32 Q2 dot Q2 R33 Q2 dot Q3. Because the Q vectors are often normal, so this is 0. How about this? This is 1. Okay, and this is 0. So therefore, we have R32 is equal to left side Q2 dot Q3. I know Q2 from the second step. A1, the third column of the matrix A. So computable. It is R32. R32 is square root 21 over square root of 2. Okay, now let me R32. I know it now. Remove the question mark. Yeah, I know this guy. Yeah, I know this guy now. Yeah, I know this guy. Now, finally, determine R3 and Q3. Move first term, second term to the left-hand side. Then R3, Q3 is equal to A3. I know it. Minus R31, I know. Q1, I know. R32, I know. Q2, I know. Now, from this equation, take two norms on the both sides. Because R3, I assume positive. So move R3 out. Too long. Then too long. Q, yeah, this is Q. Q2, too long. The vector Q2, the two norm is 1. So therefore, R3 actually is equal to this. Yeah. Now this two norm is computable. What is it? This is a square root of 7 over square root of 2. Yeah, R3. Now remove the question mark here. R3. R3, I know it now. I know. Yeah. Now finally, determine the vector Q from this equation. Move R3 to the right side. Q3 is 1 over R3 times A3 minus this. This vector, all the quantities in the expression inside the brackets, I know them. Okay, so also I know R3, so Q3 is 2, 14, negative 3, 14, 14. Yeah. Step 3, I got the third columns of Q and the third columns of R. So in summary, this matrix QR factorization is so the matrix A, the QR factorization is matrix Q is this. Uh, 42, 5, 42, and here is a 2, 14. The matrix R upper triangular zero free. The solution in this example is a typical algorithm to compute the QR factorization of a matrix. Yeah, this is a topic one. Only one theorem. Yeah, take a review about the theorem. The theorem says that non-singular matrix A. Here I assume real matrix. For complex matrix, we also have the corresponding version of QR factorization theorem. Okay, a real matrix. Any non-singular matrix can be written as a sum of orthogonal matrix times some upper triangular matrix. And this factorization is one and only one if you assume the entries along the main diagonal line of the matrix R positive, then factorization is unique. Okay, now second topic. The QR algorithm to find all the eigenvalues of matrix A simultaneously. Okay, yeah, this algorithm based on QR factorization. Yeah, let me present the algorithm. Topic 2. The QR algorithm. The idea is simple, but the result surprise all the people. Okay. Hey, given a matrix, I want to find all the eigenvalues of the matrix. How? I set A0 to be A. Then perform QR factorization on A0. QR factorization on A0. After we get the QR factorization of A0, form a new matrix. Let me call the new matrix A1. How to get A1? Multiply the two factors, but in reverse order. R0 times Q0. Hey, this new matrix actually is similar to A0. How to see similar? Okay, take a review. What is when two matrices are called similar? Yeah, we have two matrices. If matrix A can be written as some matrix, let me call the matrix P times B times P inverse. If you can find non-singular matrix P so that this equation is true, then these two matrices are called similar. From linear algebra, similar matrices, they have the same eigenvalues. All matrices A0, now new matrix A1. Q0 of orthogonal. That means that this equation is true. So move Q0 to the right side. Q0 transpose actually is Q0 inverse. Okay, so here, let me Q0 transpose times Q0. Yeah. Q0 transpose times Q0 is identity matrix. And now Q0 times R0 here. It is A0. Yeah. This product is A0. So, but Q transpose is Q inverse here. Q inverse. Yeah. Then what is the P here? You can. So the P is Q inverse. So therefore, matrix A1 and A0 is similar. The rotation similar. These two matrices, A1, A0, they're similar. So A1 and A0 actually they have exactly the same eigenvalues. So okay, now this is the first step. Okay, perform QR factorization on A0, then reversely multiply the factor to get A1. Now step 2. Perform QR factorization on A1. Okay. Then multiply Q1 R1 in reverse order to get a new matrix. Let me call A2. Step 2. Step 3. Perform QR factorization on A2. Q2, R2. Then reversely multiply the factors to get a new matrix, A3. Yeah. In this way, we have an algorithm. Okay. Yeah. Algorithm. This algorithm is called algorithm. Okay. It's called the QR algorithm. Very simple. But the result, very surprising. Okay. Astonishing. Almost all the people. Okay. Yeah. Step 1. Set A0 is A. Now, for perform a K rule. 0, 1, 2, until converge. Okay. Okay. AK is QR factorization. Then AK plus 1 is RK times QK. And it can be proved. AK. All the A0, A2, A1, A2, AK, they are similar to each other. So they have the same eigenvalues. It can be proved under some conditions. Okay. This AK approach an upper triangular matrix. The limit is an upper triangular matrix. So upper triangular matrix, what is the eigenvalues of upper triangular matrix? The entries along the main diagonal line. So when we perform sufficient number of iterations, this AK roughly is an upper triangular matrix. Then we can read the main diagonal line of this upper triangular matrix. Then we tell the eigenvalues of the matrix A. Yeah. Idea is simple algorithm is simple, but very surprising. Let me stop here.